First of all, I would like to thank you for the nice introduction. And I also would like to thank the audience for showing up and to enjoy the presentation. My name is Gustavo de Morais. I'm a member of the Laboratory for Parallel Programming of TU Darmstadt. And the title of my presentation today is Practical Empirical Performance Modeling for CFD Applications using XRP. Okay, so as an introduction and allied with our symposium, you are here again discussing CFD applications. And as an overview, these applications include different continuum mechanics applications. And I have here in the example in the figure an application using OpenFOAM. So you can see the complexity of this approach and a lot of applications that us as key users can make. And saying that, you are working with OpenFOAM. It's an open source software, and you can find in the following link. And this is open source software used for computational fluid dynamics, as I mentioned. And you have several solvers available, and the users can make different applications with the solvers. And once the complexity of the applications start increasing, it's very useful for us to use high performance computing. As I have here as an example is the computing cluster from our group from TU Darmstadt, is the Lichtenberg. And for us to be able to use such technologies, you have some challenges because those technologies are large and involve large and complex applications. And it's fundamental for us to understand and efficiently know how to scale our CFD applications when you are trying to use clusters, especially when you are increasing the number of processes you are including in our solution. And talking about solution, the solution that you are trying to present in here for make us to understand our applications is the use of empirical performance modeling, especially with our tool, XRP. All right, so as a motivation, it's fundamental for us to identify latency scalability bugs before they occur, because otherwise it's too late and you already expend a lot of resource once the problem is already facing. And as an example for us, you have here presented by this inflatable animal that represents our application. And you are using our application in such a small cluster or medium cluster. And you have more computational resource available and you want to scale our application. So, okay, it works fine for our current situation, but as we scale our code, some unpleasurable surprises can happen as presented here in our scalable animal. So basically you have some parts of computation, some parts of communication, and you can see that once the code is scaled, the communication part increases in a rate way higher than the computation. And it's fundamental for us as developers that you need and you have to find these issues before they occur. So to solve these issues, you are using scaling models. So basically they are equations that show the performance of some metrics that you have in our functions. Could be like the problem size, the number of processes, and so on and so forth. And you want to see how these input variables can change the performance of our code. And this provides insights into the programming behavior that you should assume before you start scaling the code. And here in the figure, you show how the change in the number of processes increase, how the runtime increase in function of the change of the number of processes. That maybe can show the scalability bug that I showed in the slide before. And to play this approach, you bring here our XRP, that is our performance modeling tool. So as the first moment, XRP takes a function and all the sub-tree or the sub-functions that this function has, and you perform some instrumentations. Those instrumentations, you collect some small performance measurements. That could be runtime, for example, or memory usage, or some noise resilient metrics as the number of bytes that are being transferred, and so. And once you get these measurements, you can input into XRP, and you have this performance models and how each function varies with this performance architecture that you have. And these performance models, they are human readable, so it makes very useful and easy for all developers to try to improve the code using our tool. And XRP considers any number of parameters that you may need. Here in the figure, I show 4 as an example, but you can use as much as you want. And like for example, process count, problem size, order of solver, result precision, and so on and so forth. And you combine all these measurements in a way that is independent, and you try to understand the compound effect of each parameter. And this is called multi-parameter performance modeling. As an example, I have here in the figure, in the DAO figure, 2 functions. And you can see that the parameter O, they have different contributions for the up and the down function. So the first one is additive, and the second one is multiplicative. And this is quite important for us to understand how change in the parameter O will affect the performance. As you can see, the result precision, for example, doesn't play no role in this performance. So it shows how exactly the combination of performance is combined using our tool. And of course, XRP also consider strong scaling and weak scaling. If you are not familiar with the concept, strong scaling is usually used to represent situations where the problem size remain constant and you increase the number of processors, for example, when you share the amount of work over the number of processes that you are having. And usually it's represented by Adam's law configuration. And at the same, in the different way, you have weak scaling, where usually the problem size increase with the number of processes that you are suggesting for our code. Or in other words, as you increase the amount of computational resource, you also increase the amount of the size of the problem. And it is usually defined by the law of Gustavo. So one example I have here in the figure, how it looks like. So in the first figure, we have a strong scaling approach. So you can see that for one process, you have one configuration of work effort. And as you change the number of processes, you divided the effort among the processes. And for weak scaling is a bit different. So as you increase the number of processes, you increase the amount of work proportionally. And how XRP handle all these configurations. So first, for strong scaling, you combine everything linearly, or you'll take the resource consumption and make a combination of them, as you can see, each was one single process. And for weak scaling is a bit different. So you take like the average of each process and represent it in one single process, as you can see in the figure. So for both configurations, you are expecting that our better performance would be a linear configuration in both situations, for strong and for weak scaling. Okay, so as you may have noticed, since you are using empirical performance modeling, empirical measurements are the key of the quality of our models. So, of course, you can use different ways to get these performance measurements, but the way that is more popular in our group and you validate and it works very well with XRP is using Scorpy. Scorpy is an open source and is also available in the following link. Maybe most of you already know. And they insert some measurements and instructions into the code. So they do the performance instrumentation. And you also can apply some kinds of instrumentation filtering. So you don't have to instrument in all the whole application because usually instrumentation include overhead and you are trying to avoid some huge influence of instrumentation in our software because basically include noise as well. And you can make some instrumentation filtering. So you disable some functions, the instrumentation of some functions in order to decrease the overhead. And it's usually including for small functions that are really affecting the performance of the code. Okay, and as a rule for our group that usually considers something interesting for us, they take at least 5 different measurements, and you have this performance trend of using these measurements. So as an example here, I show different numbers of processes, and you can have an idea how they scale. And also something that is very important for our applications is repeat the measurements, because usually you ask to repeat 5 times each configuration, because the measurements have noise, as you can see here represented by the red circle. And those noise, to decrease the effect of noise, usually we recommend to make some multiple measurements, and you have some kind of more not so disruptive performance. All right, so far I explained our motivations, our 2XP, how to collect measurements. So I'm going to give now an example so it will make more clear for us what you can do with XP. In this example, it's involved with a single parameter. You are using OpenFOR in our HPC architecture that I showed in the previous figuring. Especially you are using the benchmark called the CFD3D. And you make an experiment with FIAP of 624 processors in Lichtenberg, and you perform our instrumentation filtering, and you show how to interpret these results into XP. So starting with the instrumentation. So as I mentioned before, instrumentation includes overhead, and overhead is very bad for a lot of applications, increase the runtime, and also decrease the quality of our performance. So you want to reduce the the influence of overhead. So the solution that we are proposing here is to using our automatic filtering, where you select which kernels are more important for our application, and you basically concentrate in the instrumentation where is more important. And to show how this can affect the amount of runtime or the overhead of our application, these 4 blocks represented the evolution of our instrumentation. So the first block is the runtime variation using no instrumentation. So it's basically our baseline. And then you use full instrumentation in the second block. The full instrumentation instrument basically every single function. And you can see that you have an increase of 34% in your runtime, and it's not desirable. And you try to use this dynamic filtering that you select the functions that are more heavy, and you activate and deactivate the instrumentation while you're running the function. And it helps, but not significantly. So we still saw an increase of 30% in our runtime. And then you use our static filtering that you basically choose the functions that are more important, only concentrate where is the effort is interesting for us. And at compilation level, you already select and use only those functions, and you can see that you have like only 5% of overhead that you consider that is very good. And now, once the measurements are done, you can take a look at XP and see how it looks. Firstly, how interpret the measurements and so. So use this performance modeling, when using strong scaling, and you keep some parameters like the mesh size of 460 in the power of 3, 3,000 interactions, and you variate the number of nodes from 1 to 6. And every node has 1 or 4 processors per node. So you are increasing the number of processes and seeing the influence of everything, of this variation in our code. So basically in the figure, you can see 4 functions. The first one is the main function. So the main is the result of all the single functions that are inside. So you can see that the performance of the main function takes a behavior similar with the MPI communication. And once you take a look at the MPI communication, you can see that it started increasing in a way that it dominates performance when the number of processes increase up to 600. When the number of processes are below 600, you can see that you have 2 functions that are ideally scaled. The first is the precondition and the multiplication. And you can see that they have the behavior that we are expecting for computation, but the communication has a behavior that is not expecting. So you are basically showing here that using this small number of measurements, you point to you that your problem, your code, you have a bottleneck when you start scaling your code up to 600 processes. What it means is the time that you're taking for making communication, the time that you take for making communication, and you have to do synchronization, waiting stages, and so on. And this takes more effort than the computation itself, and it's not desirable. So you basically point out to you where is the problem is. And to prove that our performance models has a good quality and they show that the model is accurate, you also make more measurements to show that the performance looks what you are expecting. And you can see here in the figure, when you put more extra measurements, you can see that the scale behavior was captured even with the small amount of measurements that you show for the modeling process. All right. Moving on, we have, you can see in the GUI from XRP how it looks. So basically you take like the 4 functions that you analyze. First of all, XRP can make this combination of functions. So you have everything, the result of the encapsulated little functions inside. And you also can make like an individual analysis of each function. So that's how it looks in XRP. And you also can change the number of process, and you have like a very good representation what is going to happen with your code once you change the number of process from your application. All right. Saying that, I would like to conclude. So in other words, XRP helps identify potential bottlenecks, as you show in our case study involving Cavity 3D. The MPIR reduce is the main bottleneck in our application, especially when the number of processes increase for up to 600. You propose automatic ScoreP filter, where you can see that you decrease the amount of overhead for 35 to 5%, and also increasing the accuracy of the model. And all our solution is available as part of XRP. So I would like to invite you all to take a look at our solutions, also in GitHub and our YouTube channel. And I'll be happy to take some questions in case you have. Thank you.